The lurking behind this little window, oh, there we go. It says go live is, what is a spark? I've got a Jacob's ladder over here that they found in either the basement or an attic of one of the middle schools. And Mr. Chase got it. One of the custodians gave it to him. And it looks like the one here on the screen. So when I turn it on, there should be a spark at the bottom, and the spark's going to go up and up and up, and then it's going to extinguish, and then a new spark is going to start at the bottom, and it'll go up and up and up, and it'll keep going. And here's what's this thing? Yeah, it's a common thing in vehicles.
Oh, spark plug.
Spark plug, yeah. So a spark plug makes a spark. But the first question is, what is the spark? This is kind of hard. Like if somebody asks you, what is a flame and how does a candle really work? That's a much harder question than you think. So everybody knows what a spark is, but what is it?
Like energy.
Definitely energy, and visible. So it's visible radiation that we see. Is there any heat associated with it? Yeah, I'll click on this and then talk a little bit more about it. I can't remember what this link goes to. Electric spark. An electric spark is an abrupt electrical discharge that occurs when a sufficiently high electric field creates an ionized, electrically conductive channel through normally insulating medium, often air or other gases or gas mixtures. It's kind of weird to imagine a spark going through something solid. So what they're saying is that this this is a spark plug, and one of the things you'd have to do sometimes if you are trying to get your lawnmower or your motorcycle or whatever to run right is to adjust this gap. If this gap is too small, it's not great. If it's too big, it won't spark across it. But basically there's a really high electric field, and we'll get into the word potential later, but a potential difference across this gap. And you could just imagine it as a bunch of charge building up on one side and an opposite charge on the other. And when that's big enough, the electricity will cross this insulator, which is air. Air is not usually a very good conductor, but it can be. Let me keep reading. Michael Faraday described this phenomenon as the beautiful flash of light. All right, enough of that. A spark is created when a applied electric field exceeds dielectric breakdown strength. And let me go back. But exactly what it is, it's just I felt like I had a really good answer. So it's hot and it's light, so energy is given off, and I feel like the word plasma should be in here somewhere. Let me look for. Yeah, go ahead. So sparks with very low energy still produce a plasma tunnel through the air through which electricity can pass. So as soon as you get up to a high enough kind of a charge, this air breaks down, and basically the air molecules get ripped apart and the electrons get freed, and you have a plasma, which is really conductive. Regular air doesn't conduct electricity very much, but once the spark starts going and it heats up the air and it kind of tears apart the molecules and frees the electrons, then conduction can happen really easily. So this Jacob's ladder creates a spark down at the bottom, and then something else happens. Let me move the camera, and I'm going to start up this Jacob's ladder, and hopefully, good, nobody's in the picture. If you're over there and you can't see it, you can move back here where you can. I just want to make sure people watching this can see it. This is the classic mad scientist kind of thing that you see in people's labs. Hey.
Hi.
And when I plug this in, we're going to hear a whirring. I kind of think that's the fan to cool it off, but I'm not sure. I don't know if there's a note that says, Jacob gets a little hot, 30 seconds on, 90 seconds off, press and hold. And I'm guessing when I'm not pressing, that's the fan that's actually cooling Jacob down. But maybe that's not the fan, I don't know what that is. That was actually a pretty good one right there. Okay, so I don't know. I'm going to unplug it because that sounds like it might be doing something to it. So the spark starts down here, and there's, I believe, a transformer in here. A transformer is what you see out of the power lines that come into your house, and you might see it at other kinds of stations around town. But a transformer changes the voltage, and the voltage in a power line could be 800 volts or 1200 volts or whatever, but when it comes into your house, it drops down to 220 volts or 240 volts, and the transformer does that. But in here, I think it's taking the 120 volts coming out of the outlet and it's increasing it. So it's not maybe quite as much voltage as what we have in the Van de Graaff generator, but I think it's probably a lot more current flowing through here. We haven't really talked about current yet, but it's, so there's high voltage. Voltage is just, you can think of it as the pressure that's trying to push the charge from this electrode to that electrode. Like the buildup of a bunch of charge on this having a very different charge that makes it want to leap across. And when that gets strong enough, like I was saying, the air molecules in between, they just kind of get torn apart, turned into a plasma, which is conductive. And then the charge can flow across. And in the process, that heats up the air glows, and it also gets hotter. So the spark starts there, but as I keep holding this down, the spark travels up and up and up. Why? And then it starts again there. Always starts there. So the first question is, if these are conducting rods, and the transformer is hooked onto both of them so that it creates a lot of charge on one side and a lot of opposite charge on the other, why does the spark start at the bottom? Take a look at the two rods.
They're closer together.
They're closer together, yeah. So it's wherever the attraction between those charges on the opposite rods is, wherever they're closest, it's going to be the strongest attraction. So that's why the spark begins there. But if the spark begins there, and that's the strongest attraction, why doesn't the spark stay there? Why does it go up to places where it's actually harder and harder to leap across? Eventually it gets so high that it can't leap across, and that's why it stops. And then it restarts.
So like up there is like pulling it up, right? Like there's like...
No, but a good guess. So the first hypothesis is something up here is attracting it and pulling it up. It's not that.
Something down there pushing it away.
That's closer, but it's not really something down there pushing it away. It's something all around pushing it up. And let me just reiterate what's going on. So, and maybe in a different way. When you get enough of a potential difference, enough of a charge difference built up on the two sides of these conducting wires, then you get like a plasma that forms in between. And the plasma serves, it's almost like a new wire is created that goes across there. That air, it's not like normal air. Normal air has a bunch of molecules with, it's oxygen, it's nitrogen, and in each of those molecules, the atoms have protons in the nucleus, and they've got electrons on the outside. But when you have a plasma, the electrons and the rest of the atom, and basically a lot of the atom is just all separated. So the electrons can flow through it. So it conducts really well. It's kind of like turning air into a metal, where the electrons can flow. So it's as if, when you first see the spark, it's as if a wire gets created across there. But it's not a wire, it's made of plasma, which you could think of like a gas. So why would that gas rise?
Oh, because it's lighter than air.
Why is it lighter than air? What kind of air rises in general? This is an earth sciencey
Gas.
concept. Well, air is a gas,
Okay, they're like,
and all the air is sitting still right here. But if I wanted to make this air rise right here, I could do it without, without
The
doing
air
that.
around the spark is warmer than the other air, so then it rises.
Exactly. So that the bridge of plasma right there is super hot, and that makes it expand and it becomes less dense. So the plasma starts to rise, and the plasma is really conductive, but the air that's down below it is not. So even though these two wires are closest together at the bottom, as the plasma moves up, that's the most conductive place to go from one wire to the other. Even though the gap is growing, it's still easier to conduct electricity through that than it is across this regular air down there. So as the plasma rises up and up and up, that it's like the wire connecting these two wires rises up and up and up until eventually it gets so far apart that not even plasma can conduct a spark across that whole gap. So let me do it again. You'll see it start up down here, and my guess is it takes a little while to heat up the air around it. That's why it stays at the bottom for a while. But once that air gets hot enough, then it starts to rise up. And why do you think it has a plexiglass cover on it?
so can't jump or anything.
No, well, that's probably it too. So nobody sticks a hand in there. But it wouldn't work as well without a cover on it.
Is that why it doesn't go to the top?
Maybe. Although I don't know if it's ever gone to the top very well, even before this was broken off. But do you think it would work well if we blew a fan on it? No, because the plasma would just blow out. It would get away from the electrodes, and that would kill it. It would just, if we had a fan on this, it'd be kind of nice actually to be able to take this off and put a fan on it. And my guess is the spark would stay right down there. It might come up a little bit, but it really wouldn't get up very high. Anybody smell kind of funny smell now? Yeah, I don't know. I think interesting things are done to the air when you do this. Supposedly it produces ozone, which is good for the ozone layer, but not really good for us, but there's not so much of it, so it's okay.
How hot is it?
Ooh, let me look that up. How hot is plasma? I don't know, but I'm a Google capable person, so let's see. And I think, so to be plasma, there may be a minimum temperature, but I think plasma can get hotter and hotter and hotter. So, science of plasma. It's probably more than source. The core of what? Oh, the core of plasma ranges in temperature from 11,000 to 14,500 degrees Fahrenheit. So this is just talking about stars like the sun. So, I don't know. I don't know that there's a particular temperature. If you get things hotter and hotter and hotter, they turn into a gas, and then after that, at some point, they become a plasma. It's probably dependent on the element. Do different elements turn plasma at different... You know how there's a boiling point and a melting point? I don't know what the word would be for the temperature at which something turns to a plasma. Oh, physics stack exchange. That's going down a rabbit hole there. I don't know. I'll have to do some more research to really give you a good answer. But it's hotter than a gas. All right. Hand out the instrument notes. Anybody who got here late, there's another packet up there, the Unit 11 packet. Sarah and Anna, I'll give you one of those on Friday. We won't need them until Friday. So today's a pretty quick day. Just a few things. Tomorrow, no Google Meet unless you want to ask questions about the test, just for test review. And then on Thursday, everybody will be taking the test. If you're remote, take it remotely. If you're blue, take it remotely. And if you're gold, you'll take it here. Then on Friday, we're going to start instrument stuff, and we'll talk about this cute little cat, among other things.
So this stuff won't be on the test?
Right.
Okay.
Yeah. And notice that the packet I just gave you is Unit 11. So we're in Unit 9. Unit 10 is going to be electrical current and circuits. But I just want to start the instruments so you can have them and play around with them and do some stuff earlier rather than later. Then we'll go back and finish electricity. Okay, so the homework. This is the time to ask any questions you want to ask about Mr. Pennington's old test. So, cool. Does anybody have questions about any parts of this? Jack,
Can you go over number 6 on the short answer, please?
you multiple choice or was there a short answer?
Short answer.
What do you mean
Like
by?
the problems.
Okay, problem number 6. Gotcha. Because there is, on this upcoming test, there will be short answer. The Earth has a net charge that produces an electric field of approximately 150 newtons per Coulomb straight down at its surface. What mass object with an excess of 3.6 times 10 to the 4th electrons on its surface will have its weight supported by the field? So this is another example where we've got something floating in the air and there are two forces on it. There's the electric force pushing it up, and there's the gravitational force pulling it down. And I may rely on Mr. Pennington's work, but I want to draw a picture just to talk about the sign of this, and just to get our bearings on it. We can make this a little bit bigger. Oh well. Hold on for a second. So it's 150 newtons per Coulomb straight down, 3.6 times 10 to the 4th electrons. So here's the field. This is actually kind of this problem gives away a lot. So what he could have done is he could have said this is the electric field, and he could have said there are X units or so many 3.6 times whatever that was 3.6 times 10 to the 4th units of charge, of fundamental charge. I don't know what he would call that. Sometimes he just calls it, I don't know, Q. And then he could ask, whoop, oh, sorry, Anna. She couldn't see my screen. And he could say, this thing is suspended here. The weight of it is pulling it down, and the electric force is pushing it, is holding it up. First he could ask, what is the charge of this? But he went ahead and said that these are electrons. So they have to be electrons because the direction of the electric field is down, which means a proton would be pushed down, which means if this is going to be pushed upward by the electric force, it's got to have a negative charge. So, but anyway, he didn't ask that, he just gave that. So this is how many electrons there are. So we know this force, and there are a couple of ways to calculate. Since this is a field problem, we can use the formula, the electric field equals force per unit of charge. So in this case, the force equals the electric field times the charge. So that's this force. It's going to be E, which is this, times the charge, which is, it's not going to be that number because that's how many electrons, and each electron has a charge of 1.6 times 10 to the negative 19th, I think, coulombs. So, but if we take this number and we multiply it by this times this, which is going to be the total charge of that many electrons, that'll give us this upward force. And the downward force, mg, needs to balance that. So basically it comes down to EQ equals mg, and we're solving for m. So let me go and switch over to what he did. Number 6. Yeah, so he wrote right here QE equals mg, and then he's just solving for m, QE over g. And the charge is the number of electrons times the charge per electron. And there's the electric field, and this is g. So, Jack, does that explain it?
Yeah, wait, how do you know that 3.6 times 10 to the 4th is multiplied by 1.6?
So for this formula, we need a charge. So mass, are you okay with this part? Mass equals
No, I
QE
get
over G?
that. I
Okay,
just
so,
wanted to do
so
1.6.
Q is a charge, and this is a number of electrons, which is not a charge. The charge should always be in coulombs.
Okay.
So we're given the number of electrons. We have to
I'll convert
use
it.
this to convert it to coulombs, because each electron is this many coulombs. Okay. What else? Does anybody else have a one you want to go over, or want me to go over? Any multiple choices? Any other problems? All good? Well, I'm happy to come back to this, but if nobody's going to ask questions, I don't want to waste your time. So let me jump back to other stuff on the agenda. All right. Instrument notes, I handed that out. Review practice test. Electrophorus, I want to come back to that. I want to jump forward a little bit to the test format. They're good. Yes, Anna.
I don't see, but I asked in the chat if you can do 21.
Oh, sure. Sorry, I don't usually see the chat. I forget to open it up. Yeah, I'll come back to that right after I finish my thought here. So on the test format, there are going to be 12 multiple choice questions, 4 short answer questions. And I mean, these are not, I'm not just coming up with another way to say problems. These are actually short answer questions. And then 6 problems. And with regard to formulas, I think this is all you need. So this top left, that's Coulomb's law. And really, you don't need this one in the middle. I don't know why I included that, but I'll just leave it there since it's there. The one on the right, this is the electric field formula. So you really only need Coulomb's law and the electric field. Why don't you need the one in the middle? Does anybody know? Derive it from the one on the left and the one on the right. So if you take this electric force formula, K Q1 Q2 over R squared, and you plug all that in up here, then one of the Q's basically gets canceled out, and you get KQ over R squared. It's written a little bit differently. Usually when I write the electric field formula like this big Q indicates the charge that's causing the field, and little q is usually the test charge, or the charge that experiences the field. But it's not a big deal. And then you need to know Newton's second law, F equals ma. You need to know that weight equals mg. And in terms of kinematics, the only kinematics formula you're going to need is this one. So there's going to be a problem that in some way you're going to have to solve for something regarding some charged particle. Either give its initial velocity if you know its acceleration and displacement and final velocity, or find the acceleration with this other stuff. But that's probably going to be in conjunction with F equals ma, and then one of these other formulas, the E equals F over Q, or F equals KQ1 Q2 over R squared. So got a couple of ways to find force, and once you have force, you can plug that into the F equals ma formula. And once you get an acceleration, then you can do some stuff with this, So these will be used in conjunction, but really there are only two new formulas, the one on the top left and the one on the top right. All right, Anna, I'm going back to number 21, and I'm going to just use my camera.
Can I go to the bathroom?
Sure. And I'm glad you asked. This is one that people had a hard time with last year. So I kind of expected trouble with this. An electron travels from left to right through a small hole in a uniformly charged plate. So we don't know whether this is positive charge or negative charge. We just know the electron's going like this. Once through the hole, the electron accelerates to the right. What's the sign of the charge on the plate? And what's the direction of the electric field on the right side of the plate? So this is a cross section. If you looked at the field, or if you looked at this plate from over here or over there, it might look like this. It's just got a hole in the middle, and we're seeing the hole from a side view. I think that's how it's supposed to be. And this plate is either all positive or all negative. And the key is once it's through, so when it's right here, it's going to accelerate to the right. So it's got positive acceleration, which means there's some force to the right. There's a net force going to the right. And once you know that, there are multiple ways to think about this. One is you could say, all right, it's being forced to the right, and it is an electron. It's got a negative charge. So what kind of charge on the plate would push this away? Negative, yeah. So like charges attract and like charges repel, opposites attract. So if this negative is being pushed to the right, then this plate is negative. And then once you got that, you could draw field lines, the electric field lines. And when I draw electric field lines around something that's negative, do they go out of it or into it? Into it. So let me just draw those now. They're going to look like this. And this doesn't really matter, but this is what the electric field would look like on the other side. So in this region, right over here, the electric field is pointing to the left, and the plate is negative. So the charge on the plate's negative, electric field is leftward, on the right side of the plate. On the left side of the plate, the electric field would be to the right. Anna, does that do it for you?
Yes, thank you.
Okay, you're welcome. Any others? Well, I've got this out again. All right, so let me, Anna and Sarah, if you have any other questions, just blurt them out, because I'll forget to look at the chat. Up to here. Oh, I've got to hand out the instrument notes twice on here. I was really worried about that. I want to talk about the electrophorus and some charging of stuff again. So I've got the electrophorus right here, at least part of it, and I've got, instead of what I had before was an acrylic plate, and I had some wool, and I had acrylic plate, wool, and this thing, and I could charge this up, but today I'm just gonna, I've got rabbit fur, and I've got a balloon. I've got this nasty one that's already got a bunch of rabbit fur on it, and I've got the other one which is out of reach. So what I want to do, I want to charge up this plate so that when I do this, it goes. And I want somebody to tell me how, using these three objects. The rabbit fur, the balloon, and this thing. This is conductive. This handle is an insulator. Anybody want to volunteer?
Rub the rabbit fur on the balloon and touch it.
So Ollie's saying rub the rabbit fur on the balloon. which I'm happy to do. I love rubbing rabbit fur on the balloon. Okay, I get enough of this. This is one of the most, my computer doesn't always work, but this always works. And alternatively, I could rub the balloon on the rabbit fur. All right, so step one complete. What do I do now, Ollie? Touch the plate to the balloon, like this. Okay.
Take it off. Touch your finger to it, but on the one that's holding the black handle.
Mm-hmm.
Touch your finger to it, and then touch your other finger.
Didn't work. Something went wrong, and that's okay. It would be kind of disappointing to me if we got it right first time. Yes, Jack. What do I do differently?
Put your finger on the metal plate when you touch to the balloon, so it conducts the energy into the plate.
Okay, so I'm rubbing this on the balloon, and I'll put the plate on the side where I did this before, but put the plate there. Now what?
Put your finger on the metal plate.
Touch. Ooh, did you hear that? Touched it with my finger. Now what?
Now take it off.
Now,
Take
like
your finger off. and
like
then-
this.
No, like lift your finger off.
Let's see if this will work. Will this work?
Probably.
No. But if I had not been a pain and I had listened to what you really meant rather than trying to misinterpret it, I think it would have worked. Okay. So there's that. Put that on. You hear that? That got me. Okay, now what do I do with my finger, Avery?
You take your finger off the plate,
Okay.
then you remove the plate.
Then remove it. And now if I touch the plate, it should shock me.
Yeah.
We get it. Unfortunately, there's no microphone in the GoPro. But it did. Can you hear it out there?
Yeah.
Sorry, Anna and Sarah, you probably couldn't hear it. I can maybe put it up to your camera and then you could hear it. You can actually hear this better when I initially do this. Let me put this up. So if I put this right here and I touch this, it shocked me twice as my finger was on the way. And it stopped, but now when I let go and do it again, it shocked me again. All right, so anybody want to explain what's happening? Because on the test, you're going to have some kind of a problem where you have to explain how something is charged. Avery?
So the rabbit fur, when you rub it on, it charges up the balloon with negative.
Some kind of charge. We think it's negative.
Yeah. And then when you touch the plate to it, and then you touch your finger, your finger grounds the plate, so then it will take some of that charge.
So the plate's a conductor, and if the balloon is negatively charged, what's happening to the negative charges in the conductor right now if the balloon's negative?
I don't know yet.
So would they be attracted to the negative balloon or repelled by the negative balloon?
And push into the plate.
So they're pushed into what part of the plate? The bottom or the top?
Top.
They're top. So the top has an excess of negative charges. And they really want to get free. It's like, I don't know, they're on some ship with other creatures they don't like. And then when I touch it, then what happens?
The negative charges go into your body.
Right. So they are able to get farther from the balloon by going into me. And then when I remove this, what happens to the plate?
It gathers a bunch of negative charges because the plate is now positive and the balloon's negative.
Everything was good up until then, but the balloon charges, I don't think charges are going to flow from the balloon into the plate very easily. Anybody know why? Is this balloon a conductor or an insulator? So it just doesn't conduct very well. I'm a better conductor than the balloon. My skin is, so the charges can flow into my finger. But right now, if the balloon were a really good conductor, more charges would be flowing into the plate. It'd be negative again, and I could keep going every time. So what's the plate's charge now? It's positive. And that's because initially, when I put it on the negative balloon, the negative balloon repelled all the electrons up to the top of it and tried to push them away. I gave them a path to actually leave the plate. Not all the electrons. There's still a whole bunch of electrons left in there, but a few excess ones. They left the plate into my fingers, so now there are fewer electrons than there are protons. And now I've separated this. What's the charge of the plate now? Positive still, just what it was before. And if I touch it, why does it spark?
Because you're still negative from the electrons and the plate's positive.
Close. Anybody want to modify that a little bit?
You're neutral?
I'm still touching the ground here, and even if if I had wet bare feet, that would be even better. So I'm still grounded. So I'm kind of neutral again. But so if I'm neutral and I touch this and I get shocked,
The electrons are leaving you in the ground.
right? So they're flowing. This is now positive. So there's a higher concentration of negative charge in me in the ground, and that flows into this positive region. So this is attracting electrons back out. So let me do all the steps again. So the rabbit doesn't like electrons, basically, gives them away to the balloon. The balloon's got a bunch of electrons here on the surface. Those electrons are going to repel other electrons in this conductor up to the top. It's not electrons going from the balloon. In fact, I think if I could do this without even touching the balloon to the plate. See how this would work. I don't know if it's close enough to do. That's not. Yeah, so sorry, I lost my train of thought. This gets negatively charged. Those negative charges on the balloon push the electrons up to the surface. Now I give a path for the electrons to jump into my finger and go to the ground, because the ground is less negative. Now I let go. Since electrons left, this plate is now positive. The ground is neutral, so that positive plate is going to pull electrons out of the ground, which is what it's doing. So electrons first come out of me because this has too many electrons, and then later electrons come into me like this, and then they go back out of me into that. Whew. Let me run another scenario by you, just from the notes. I think that this is a new packet where I haven't drawn on this before. Actually, it's got information there I don't want you to see. But I'm going to ask you about a couple of the conductors from the first notes we did. So if you have this is an insulating stand, and this is a conducting sphere. And then we've got another conducting sphere with an insulating stand. And you charge up a rod and make it negative. What I want to do is give this a positive charge. No, I guess that's tricky. Yeah, sure. I want to give this a positive charge without touching it with this rod. So can anybody tell me a way to give this a positive charge? This is a neutral conductor. Both of these are neutral conductors. We've got a negatively charged rod. I want to give this a positive charge. Can anybody think of a way to do it? And what process would you follow?
Oh, if you want it positive, you just have to have less electrons than protons, right?
Yes. Yeah, you need to have more positive charges than than negative charges. And which one are you actually going to be able to manipulate, the positives or the negatives? The negatives. Let's assume you're not chipping any off of these conductors. So you can move the negatives, but you can't move the positives. So how do you make this positive? I can think of two different ways. There's one kind of simple way, similar to what we just did, to make this positive. Yeah, Jack?
If the other sphere is more positive, the electrons will go to the other one, trying to convert it to become less positive.
So just tell me step by step. I want to make this positive. How do I do it?
You make the other one positive.
How do I make that one positive?
Oh, I don't know.
This one's neutral, this one's neutral. I just want to make this one positive.
Would you touch the rod with the negative charges to the other one?
Okay, so let's say I touch the rod with the negative charges to this one. And what do you think that would do?
It would make it negative.
Yeah, if I touched it and this is negative, then some of those charges are going to flow into here. So this is going to become negative. Now you can do all this without touching, but so that sort of gets us two rods now. We just had one rod and one neutral thing, and now we've got two negative things. So let's back up there. Let's not do that. And I'm going to institute, if I didn't make it clear, the no touching rule. Again, how do we make this positive? Anna, or wait, Sarah left. Sarah lost. Sorry, Anna, if this is just awful from your end. Do you have any ideas, Anna? How do we make this positive using this negative rod without touching it to anything?
I'm not really sure.
That's okay. Leslie?
I know how to make the other one. So if you take the first one, and bring
This
it
one?
closer, the electrons will be repelled and go towards the other one.
Okay, so bring them close together.
Yeah.
How close together?
Just enough so then the electrons can jump through.
So if I did this, and I put the, now where do I put the rod?
You just have to put it near it, so then,
Like here?
yeah.
So if I did this, and both of these were conductors,
Yeah. Then I know how to make that one like really negative.
would, this is air right here, would electrons leap across here?
No, I guess
No.
you have to like touch.
Yeah, so if you just did this, what would happen is this side would become more negative and this side would become relatively positive, but all you would have really done is polarized it. So if you connect them, if you bring them really close, I'm just going to make this, change the shape of it so I don't have to erase the whole thing. Then that's going to push electrons from here all the way over to this side, and that's going to deplete this side of electrons. All right. So what do I do now?
And then I'm trying to figure out if you need to separate them first, then ground it.
So if you just separated them at this point, if you grab this insulating stand and move this over, would that change the charge of this at all? I don't think so. It wouldn't. So you could separate it, and what you would have then is these charges would all spread out. This would be negative. And what about the other one? What would it?
That one would be positive.
So you figured out how to make one positive, but it's the wrong one. So the only thing you would need to do differently is what? Like bring this one over here, or take this wand and put it over there to begin with on the right side. So that's one way to do it. But you can do all this with just one of these. So if you have this negatively charged rod, and I want to make this positive, I only need one. What do I do?
Ground it.
Ground this?
You
Jack?
have to put a thing, like some way for the electrons to escape out of the ball thing.
So if I attach a ground wire going in here, going into the ground like that,
Well, does it even matter where it's going? Or does it have to
it's got to be going to some place. It needs to be going to some place that would the electrons would want to go. But then what do you need to do?
Touch it to the wall.
Touch this to that?
Yeah.
You can't touch it, that's against the rules.
Bring it close.
Yeah, bring it really close. And if you do bring it really close, then the electrons that are here, they're going to get repelled over here, but they're actually going to want to go as far away as they can go. So they'll come out. So once they do that, then you can disconnect the ground wire, and then what's left behind will be a relatively positive thing. That's basically like the electrophorus. So I'm just putting this, you know, this balloon. Ooh, this balloon is like that negative thing, and this is like the sphere in the picture, and my finger is like this ground wire here. So if I touch that, and then I remove this, now it's positive. And then once you've got a positive, once you've got something positively charged like this, if you connect it to the ground again, then electrons are going to flow back from the neutral ground into here, the other way. Okay, I won't punish you with any more of that, but be ready for some questions about that, about charging things by induction. Make sure you understand why balloons stick to the wall, even though the wall doesn't have a charge. It's because it's polarized. I don't think we need to do Mr. Pennington's 4-minute drill. I don't think it's really that useful. It's just about some formulas. That's really it. I don't want to teach anything new today because we're just going to do the test next, and I don't want to load you down. We'll start instruments on Friday. That'll be the next new thing. Anna, do you have any other questions?
No, I'm good, thank you.
Okay. If anybody wants to, if you want me to make up some example problems using any, similar to any other kind of problems that we've done, I'd be happy to do that. But I could also do that tomorrow too, if you come to the review. Are we good?
Yeah.
Okay. See ya, Anna. Signing off.
Can we mess with the,
The Van de Graaff generator?
Yeah.
Sure. Let's leave it back there though. Just leave the call. What do you want to try? I was trying to figure out whether it was positively or negatively charged by throwing the balloon at it earlier. And it repelled the balloon after I rubbed it with rabbit fur. But it seemed like it, then I did that with the balloon where I didn't rub it with rabbit fur, and it's the same thing now.
well, didn't it charge it up?
I guess. It must have charged it really fast. So, is this off or on? Guess we'll find out. I'll leave this here for you to enjoy. So this is the ground. When it first starts up, and it'll just go. Doesn't really want us to just move it apart if you want it to really charge it. I'm not really sure what this point is for all versions. Underground. If you want a really nice shot, you can grab this. That's it. There you go. Can you feel it pulling? If you hold one of those pie plates with the flat side close to it, you can feel it pulling too. Yeah, pull that away and hold it next to the vent right there. It'll shock you. It won't kill you. Unless you have a heart condition. Can you feel it pull? Oh, come on, Sam.
No, we're just talking about water.
It's okay, Sam. keep fighting it until you touch it and hold it there, then it doesn't hurt anymore. It hurts a little bit on the way to it. Yeah, touch it, there you go. Now that you're there, it's fine. If you touch him, you're fine. Actually, it works best if you stand on a bucket or something, and then you can, if you stood on this chair and then reach out and touch that. So stand on the chair for a while. And you can just touch it with your hand.
Oh, your hair.
Oh, look at that hair.
And I can feel it on the glove. Oh my god.
You want a picture?
Oh my god.
Hair, bro.
I don't want to get my phone too close to it. You look pretty back.
I want to do my hair. Wouldn't it go like all the way up?
I don't know. His might be dry.
Does that hurt?
Not.
Does that hurt?
So go ahead and ground it before she gets there.
Yeah.
And then, whatever. It's more fun for us if you use the plate.
I don't want to be shocked. Am I gonna get shocked?
Wait, how do I ground it?
This is a good test.
Am I gonna get shocked?
Not if you do it right.
How do I do
So
it?
how do you not get shot?
I put the plate here before I turn it on.
You first ground it with this. So if it's charged up, you just want to, this goes right into it. So that's grounded. Now if you get up here on the chair, it should be a pretty good install.
Sorry.
And I think you'll need this, but, so just put your hand on it. Get a good connection. You move it closer.
Dude, I know.
Yeah, just
Really
flat on your hand.
So then when I take my hand off, will it shock me? You already
It
I
should,
am never ready for pre-cap.
Yeah. I don't feel good.
they're starting to stand up.
Like the paramedic.
Oh, yeah, look at that.
Been since like mid-April.
Oh my, all the same.
Yeah.
You're sort of,
Like I
with one
literally
hand,
forgot
just
that
gonna do
it was
that. Oh, yeah, there you go.
I didn't, I thought that was.
And then she mentioned it.
And I was like, wait.
Well, let's stand it up. Oh, that's better. It's not quite like Jack's was, but it's still pretty good. Let's see.
Yeah, it's mostly just me
Oh,
reviewing.
nice.
Oh, it's even better now.
Me reviewing them in chapter.
So if you,
You like,
I cannot remember.
I wish
I mean,
Sid
I've
were here.
got
She can reach out and touch it.
Like the we don't really
Oh,
know
it's
that
getting so
many.
good.
No.
That's like the
Okay.
sine and cosine twos and the
Why are you
sine
so
and
much
cosine
better
circles.
today?
so can I like a head thing or like
That was confused.
Oh, shoot.
They're all too big.
Oh, just a bit. Okay, so
Why?
normally we turn it off. I'm afraid to turn it off though.
Why is that something?
You know what, where's my little, I just don't want to get anywhere close to this. That sucks. Here,
So I'm stuck here.
No, yours charged up. I think if you do this, watch this. So in just a second when I give you the word, just move your hand way back and farther from this, and then and then you, look at her hair. Wow. That's the best ever. Okay, so jerk your hand away now. Okay. We're all good. Didn't we try this the other day and it didn't work well?
Yeah, Jack did it. And it was
Yeah. Anybody else want to? Avery, you want to try again? It seems to be working better today. Yeah.
You sure you don't want to try it with your phone in your pocket?
I'd rather not.
What happens if you have your phone?
Oh, it's probably fine, as long as you don't touch it and spark your phone.
I didn't even try
So
it.
here, I'll start
I
with that
know.
too.
You know, my parents paid a lot for that phone. I don't really want to throw their money out the window.
I should be reviewing. then loops, and then flatten back.
And it could be, you know, different hair, depending on what kind of products you use and all that. Like, yours might not, you might have thicker strands or something. You feel like you have thin
You
strands
also
of
have
hair
to
or
do,
thick strands of hair?
spiral.
Debbie?
Probably
You
pretty
don't have to
thin.
graph those
Yeah.
like
Yeah.
Apparently
lines.
red hair people are the best for this.
Really?
Or maybe they're the worst, I can't remember.
Well, red hair, like,
Is
don't
red
they
hair
have
thinner or
like dry
thicker?
hair? Like their hair
I
is
don't
so.
know.
Oh, don't worry, I don't know what I'm doing either. I'm in the classroom. So, I'm doing
Mine got really good. You didn't get a picture.
Oh, we also
It was
get to
really
make
good.
flowers.
No, do you want to do it again?
Yeah, sure.
Flowers is also something.
Kind of ruffle it a little bit with your free hand.
Yeah. It got good after a while.
Yeah.
Your head was real nice, too, like,
You're just charged way up.
Oh,
Your hair is not as staticky, which is probably a good thing overall, is, you know, it's super staticky hair. Doing it, you know, it's hard to go. See a bunch of little strands. And if at this point somebody came by and you gave them a handshake.
Hey, Julia.
Oh, yeah.
Over here.
Shake your head again. Ah, it's a lot better. Here, I'll get a picture of this. Mostly this side is doing well.
What are you doing?
I think it's still growing.
I do not remember that unit. That unit was,
It's kind of pulsating.
did I think, I did not know.
Is that you or is it
Okay,
not
hold
its own?
It's
Oh, look, and listen to the machine, how it kind of goes. Wah, 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 wah. And it's in time with her hair. Kind of reminds me of a lionfish. All right.
My
You had
little
enough?
rolling plant has
Okay.
got like,
So, just like she
does do it, but it's a lot of like. I just love how like our schedules are just being thrown off a little bit. I think it's like the final thing, probably.
Yeah. Like getting in all of it. And making sure that seniors get their graduation requirements. I still need a gym.
I'm getting that over so I don't know what it is.
Do you ever take activities in the benefit?
That one was the one that got.
You're about to charge
me.
me, you're gonna get.
Well, like I.
Yeah, I'm in
like,
it right now.
Yeah, you can do that. Now, your hair, as soon as
Yeah,
you jump
so I
down,
missed like
it'll
the
just,
actual fun part of like doing planning and I was so sad. And so I was
you wanna do anything else with it,
Yeah.
it's all yours.
that's the one I had and then I was like, I had to take the class, so I'm just like, I'm just going to do right here, that's like, I can do that.
Do you wanna try it?
So are we just taking the test
What?
remote?
Just the test is on Thursday?
Yeah, so we're just doing it at home then?
Yes.
We're not waiting till Monday?
Right,
Okay.
we'll just all do it.
Oh,
Yeah.
I said, how does it work again? Like the.
I'll show you. We can take it apart. At least part. The bottom part you can't see very well. Yeah, it's really complicated, but if anybody wants to see the inside, the inside the top. You hold that for a second? Here's the. The bottom's got the same thing. Yeah. So this, I don't know which kind of roller is which, but there's one kind of roller on the bottom and another kind of roller on the top. And in both cases, they're these little, they call them cones. Just metal, it's a metal mesh with little tiny teeth at the top. And there's the same thing at the bottom. So when this starts to turn, the belt down there rubs against the roller. And one of them is like rabbit fur and the other one's like a balloon. So the belt, which is going like this, you can actually, I don't know if you can hear it, it's kind of crackling a little bit. The belt, as you do this, takes some of the, let's just say it takes electrons, and that leaves the roller positive. And the electrons go up here. But that really isn't enough to charge up the dome. And that takes some electrons up here. But as soon as that happens, the roller becomes positive and can't give up any more electrons. But there's one of these things connected to the ground wire. So it's really close to that roller, and electrons sort of, you can just imagine them trying to get to the roller. So they build up and they build up on these little points, and charge shoots across to try to get to the roller, but the belt is in the way, so it just hoops the belt. So this is spraying charges that are trying to get to the roller, but they hit the belt, they get stuck to it, and then they go to the top. And then when they get to the top, instead of having a roller that, you know, in the bottom I was saying the roller wants to get rid of electrons, and You know, Captain Sphere would not have struck fear into the into mariners like Captain Hook. Realize it.
Have a good day.
You too. Wouldn't it be funny if Captain Hook had been Captain Sphere?
Oh my god.
Not scary at all, really. Just weird. Rejoin.
What is that? Oh, is that the Jacob's ladder there?
That's the Jacob's ladder, yeah.
Why is there a hole in it? Is it gonna
Oh,
explode?
I never stopped recording.